Thank you. So thank you, Professor Simply, for this nice introduction and for the opportunity to present this work that is very much on our minds all over the world, I think, in the last couple of months. So I've been giving a lot of talks, and everyone else in natural language processing to sort of suddenly the whole world wants to know what's going on with these kind of models. So here's some footage of ChatGPT in action. So let me click the right button. So this is a nice little art project, but of course we're interested in models such as ChatGPT, the Bing search, the chatbots that are behind that. But many other institutions have launched in the last few months chatbots and large language models that are that have similar capabilities. And almost everybody, I am assuming, in the audience will have actually seen examples of things that ChatGPT and other large language models have produced or played with the technology themselves. But here's just to get us started. Here's just like one example that made me smile in the tsunami of examples that we saw. So my colleague Ethan Mollick asked Bing Chat to write the first chapter of Genesis as a corporate memo. And the chatbot sort of obliges and does a very good job. To all employees from GOS, CEO, subject, creation project status report. Dear team, I am pleased to share with you the progress of our creation project for the past week. Here's a summary of what we have accomplished so far. On day one, we initiated the light and darkness differentiation process. We branded the light as day and darkness as night. And this was a major milestone for our project as it established the basic framework for our work environment. On day two, we implemented a dome in the midst of the waters and segregated the waters above the waters from below. And it goes on and on and on. Of course, it does the full 7 days, and it does a wonderful job of making fun of CEOs and their corporate memos. And this is all nice and fun, but then if you present the same technology, something that is actually on a topic that you know a lot about, so many of you, I'm assuming, will be linguists. I also have a long-standing interest in language and the evolution of language and its relation that language has with communication in other species. So in my playing around, I asked ChatGPT, write a comparison between human language and birdsong, focus on the dialectical variation and the confusion this may generate, and also include the developmental stress hypothesis. And you get you can enter in an interesting conversation with a chatbot like that. And but at some point, it sort of produced it gave me this back. Human language and birdsong share some similarities when it comes to dialectical variation and the confusion it may generate. Just as different human populations may speak different dialects, different bird populations may sing different dialects. Okay, so far so good. But then at some point it says, similarly, it has been suggested that dialectical variation in human language may be the result of genetic or environmental factors that affect language development. Now, this is where linguists will draw a line, because there's linguistics has discovered a lot, and we are very interested in genetics and language. But I think no one is seriously actually suggesting that it's genetic variation that leads to dialectical variation in languages. So this is one example of what we call the hallucination problem, and the problem that is that these chatbots, these large language models, actually produce true and untrue statements with the same uncanny confidence. So when you first interact with these machines, the first thing on your mind is also, if you've been in the field for quite a long time, is like, wow, how is this even possible? How did this happen? And when did this happen that suddenly these AIs have become so incredibly fluent in natural language? And then when you play a little bit with it, and you've heard enough of the hype, then you also start to wonder, like, why does it actually fail so spectacularly sometimes, right? How does this hallucination problem arises if they can solve all of these other problems that are needed to sort of generate language fluently? Why can't they do things that seem so straightforward for us? And specifically for today, I also want to talk about the question, like, what does all of this really mean for linguists and for cognitive scientists? Like, do these models actually have relevance for our linguistic theories, for our theories of how the mind or the brain works? And do we, as linguists and cognitive scientists, actually still have a role in shaping these models and perhaps in society's response to these models? So if linguists and cognitive scientists are asking this, like, be assured that even academics in AI departments are asking this. So here's a snapshot from a paper called "Survival Strategies for Depressed AI Academics" that was doing the rounds in my field in the last couple of weeks. All right, so what is going to be our role? What is the role of linguists and cognitive scientists in this field? In what ways are these models relevant for our fields? Well, I think one useful way to think about this is to sort of go back to sort of classical diagrams of what the distinction of labor is between language acquisition research and linguistics that studied adult language. And then I'm thinking about the little diagrams like this, where we often have talk about the primary linguistic data that is being offered to a child. The child is learning language, and then we have the acquisition process, and and somehow by processes we still do not understand in all its detail, we arrive at, say, the mature language system. And if the primary linguistic data is different because we're learning from a different language, then of course we also end up with a different mature language system. So there can be a lot of variation between, as we all know, in linguistics, between languages. And between both between the data that children are exposed to and the mature language systems that they end up with, but there are also constraints on variation. So in the scope or in the space of all the possible mature language systems that we might learn, there's variation, but there's this constraint. There's a sort of boundary beyond which we don't find natural languages. Now, if we put sort of like these new systems into similar diagrams, we'll end up with something like this: that we have the training data that is being presented to a large language model. We have this a learning process using all this fancy modern machine learning techniques, and we end up with what we call a large language model, a trained large language model, which is largely like a black box machine. Now, there are major differences between the training data that children see and the learning process that large language models go through versus the one that children go through, and there are also major differences in the sort of the systems that are learned. But what I'm suggesting today is that we should think really of this as sort of like somewhere in that same space of all the possible systems. We can also sort of say, like, okay, here are the language, if we want to reuse that term, that these large language models have acquired, and they're clearly different from those of natural languages, even though if they were exposed to the same kind of data. But they are also very interesting systems that sort of like deserve a study on their own right. And in fact, one of the main messages for today is that I think they deserve being studied by linguists with linguistic methods, linguistic methodologies, and the rich, based on the rich tradition that linguistics over centuries has built up on what proper ways are of making sense of the mess that natural languages tend to be. And so we should one other message I will have today is that we should sort of pay attention to these differences, but we should also be looking for commonalities. We should also sort of see as like, is there actually something we can learn from having this sort of parallel system to natural languages and natural language learners? Is there something we can learn from it? And in particular, I think it would be really wonderful if we start working towards an overarching theory, not just of how human languages work and how human language acquisition works, but an overarching theory that can describe, say, how language learning in general can work, whether or not we're talking about these artificial setups or the normal setups. Okay, so that's the grand goal. Let me start with end the introduction and actually dive into a little bit more details, and start with that question: how did this happen, and when did it happen? Well, so for the world at large, ChatGPT was a big shock, and it was also a shock for people in my field. But maybe a little bit less. We were a little bit less shocked than most people in the world, because we had actually been watching in amazement already for a couple of years the growth and the development of large language models. And in 2018, when we called something large, it was like 100 million parameters. The model was defined by 100 million weights, numbers that you needed to specify. And also the data sets were in that same order of hundreds of millions of words that are being used. But since 2018, we've seen this sort of arms race between sort of the big corporations that were trying to sort of build this technology, and we've seen this sort of exponential growth. So if you plot that on a logarithmic scale, you get a straight line, and it really looks like a straight line between 2018 and 2022, where we see that the 100 million parameter models from 2018 are now replaced by models that are in the 100 billions of parameters that have really become, in just this few years time, 1,000 times larger. And with this sort of increase in the size of these models, we've also seen an enormous increase in the size of the data that they need to be trained, and we've seen an enormous increase in their capabilities. Now, this whole development, of course, started with the work of Claude Shannon, who already demonstrated in 1948 that by increasing sort of the length of the basic units that you take into account, so-called n-grams, you can get increasingly good approximations of English. So a second order, a bigram, what we nowadays would call a bigram model, that he simulated with probably a statistics book and by throwing dice. But in his paper, there are these things like, there's this example: the head and in frontal attack of an English writer, that the character of this point is therefore another. So it's meaningless English, but it's sort of like, it's actually surprisingly fluent. It sounds surprisingly, and that was already very surprising at the time, that it sounds surprisingly like it's grammatical English. If you look at longer sentences, you immediately spot the grammatical errors. In 2015, we had another milestone with this initially a blog post by Andrei Karpathy, who showed that LSTMs trained on Shakespeare could actually generate really convincing, grammatically very correct and text still it's quite meaningless text that sounded very much like it was if you didn't pay too much attention, like it was actually Shakespeare. But for us in our field, sort of the big shock was during the pandemic and during all the lockdowns. Suddenly, while we were all busy teaching our students online and trying to keep the universities running, OpenAI suddenly released GPT-3, and there were this sort of amazing examples of the completely coherent, long, fluent text that it could produce. So, what made all this possible? I would say that from a high-level perspective, if you want to understand what are the main innovations, the main new the things that went into building this technology, it's four things. The first thing is scale and just pure scale, just making these models so incredibly big. And we can reach that scale because the core of these models are trained with something we call self-supervision, or the next word prediction task. And self-supervision scaling up would be then the first key innovation that's behind this technology. The second is algorithmic. It uses a particular, all of these big language models use a particular algorithm called the transformer. A third big innovation is what we call in-context learning. And the fourth would be reinforcement learning with human feedback. And that was really the big shocker, and things that companies like Google and other companies were really a little bit behind on OpenAI, and why OpenAI and Microsoft managed to sort of rush to the front of the development. So let's go over those four developments in turn to appreciate what's happening here. So let's start with self-supervision and scaling up. And so the self-supervision really is a very simple idea, and that idea goes back to Claude Shannon, who defined basically the first language models. And so what the language model is, it's a model that can predict how a sequence of words will continue. So the basic setup is something like this. We start with a sentence in our training data. So that could be just a sentence. It's hot. Open the. As you see here on the left of the screen. So if I ask you, it's hot, open the, then every fluent speaker of English can suggest, oh, window or door, that these are appropriate things to open when it's hot. But what we do is we actually present this to the language model rather than asking humans here, and we present an incomplete sentence to the language model. And then ask it to make a prediction. And initially, at the beginning of training, this prediction will be very bad, very low quality. So it might predict all kinds of different words that might follow. But so once we have collected the prediction from the model, we can actually check in our training data what the actual next word was. And based on the discrepancy between the prediction and the actual observation, we backpropagate, as it's called, the error. So we change all of the potentially hundreds of millions of parameters of the model a tiny little bit, just to make sure that the next time we are in a similar state, we don't make that same mistake again. And we do this. We don't do this once. We don't do this twice, but we do this literally billions of times. So the training is time consuming, but this is where all the computing power is going into. We read in enormous amounts of text, and we use it to sort of like over and over again derive a prediction of what the next word would be, and then making fixes in our model to make that more likely. Now, 10 years ago, we were convinced that this was was an interesting task, but that it would never take us to sort of like actually solving English or any other natural language. just because it was so incredibly difficult. There's going to be so many reasons why the next word is window or door. You don't. It's not only that you need to know about the grammar of English and about the semantics of words and about everything that we consider linguistic knowledge, but you need to know a lot about a lot of world knowledge, and you need to actually, to be able to make that prediction correctly, you actually need to sort of know almost everything. So 10 years ago, we would call that AI complete. This is actually a problem that is so hard that we will never solve it, because you really need to solve the whole problem of intelligence, of how to simulate it in a computer to solve it. And the big discovery, really big discovery of this field in the last years is that it's almost the other way around. Like by just consistently training on the next word prediction, we get these models to learn not just the rules of English and the meaning of words and lots of grammatical constructions, but also acquire a lot of world knowledge, everything that it needs to actually make this prediction carefully. And that's been very intriguing, to say the least, to be part of that development. So I said a couple of times already that the training sets are just enormous. And just to drive home about how big that is, I made a couple of animations because it's easy for us to think of like, oh, millions or hundreds of millions or billions, and what does it still mean? But when we consider like 100 dots, and that I put on the screen, and so every dot here would be imagine that every dot here is a word. Then we are on the scale of things of a memo, maybe a very short corporate memo, or a little blog post, or a very short conversation where we use just 100 words. If you multiply that with 100, then we have a lot of dots already on our screen, and then we are in the tens of thousands of words. And that would be, say, the scale of a book, or the amount of words we're all using in a day or in a few days. Right? If you multiply that with another 100, then we are actually at a million words, and that would be enough to that would be the number of words that you find in a collection of books, or that the number of words that we hear or use over years. If we multiply that with another 100, then we are in the hundreds of millions, and that would be the number of words that you find in the entire library, or that the number of words that you encounter in the entirety of your lifetime. Now, we're not there yet by far. If we multiply this with another 100, then we're in the tens of billions of words. And then we're actually approaching only then are we approaching the size of Wikipedia, English Wikipedia, which if we multiply that with another 100, then we're in the billions of words, and then only then are we actually at the full size of Wikipedia. If we multiply that with another 100, then we're in the trillions of words. And only then are we at the level of the training sets that have been used to train these large language models. So for GPT-3, it's been reported by OpenAI. They say that they filtered out of almost 1 trillion words, they filtered out the 300 billion words that made the data set what was most promising. So the size of this is just absolutely staggering. It's million times larger than the number of words that we encounter in our lifetime. And so that brings us to one of these very, very big differences between what these models, how these models work, and how they are trained, and how humans are trained. So they don't. They feed on the outputs of literally millions of individuals of the text that they have put on the internet. However, I would say, like, let's not rush to conclusions from these differences in scale between humans and LLMs. So on the other hand, on the one hand, we have to be really careful to sort of draw conclusions. Like I think people are too quickly sort of ascribing competences to these language models, because these data sets are so large that we actually do not know we have no control over. We cannot check whether all these nice witty examples that people produce actually have an equivalent in the training set. It could very well be that there is already the Genesis written as a corporate memo is actually already in the training set. We have no way of checking because OpenAI is not giving us access, not a search tool to the training set that they have been using. And so we actually don't know the degree of abstraction that is actually learned with these large language models. So that's a word of caution. And we know that humans, including all of us, including scientists, have a tendency to attribute knowledge, intelligence, and sentience to things that behave in a way more than it's appropriate. And so this is a famous video from the 1940s, I think it is, for experiments for people sort of like just from a little animation of triangles and circles moving around in a particular arena are already sort of willing to sort of attribute a lot of intentions and sentience and knowledge to the individual actors. On the other hand, we do have a lot of solid evidence for what we call compositional generalization with large language models and for knowledge of linguistic rules. So we have to be careful not attributing too much, but we also have to be careful by dismissing this too easily as like all these models are just repeating sort of what they are trained on. So just to, I won't be talking a lot about my own work, but just to give one example of work what we have done to sort of show that these models actually have learned an awful lot about grammar. This paper, Probing by Priming, that appeared last year in the Transactions of the Association for Computational Linguistics. And what we did is we borrowed a framework from psycholinguistics, structural priming, and and one of the things we played with was dative constructions. And so what we could show is that you can actually prime a large language model with a double object dative construction. So if you give it a sentence like a rock star sold an undercover agent some cocaine, then if you then ask it to compute the probability of the next sentence, and you control for lexical overlap, semantic overlap, and all the things that psycholinguists also have to control for when they sort of try to use priming as to collect evidence for knowledge of syntactic or structural constructions. What we find is that most of the large language models will look like a very clear effect of priming. So they find after the yellow sentence, they find the green sentence, a man is reading a boy a book, more probable than they would have had if they had heard another sentence before. Whereas they find a man is reading a book to a boy, that uses the prepositional dative construction, less likely than they would have had if they had seen an other prime beforehand. Okay, so we have to be nuanced. These models have actually learned syntactic abstractions that are really relevant, that could be really relevant for us linguists, but we have to be also very careful because the training sets are so gigantic that it's impossible for us to imagine to have good intuitions about what is actually in there, and what is not. Okay, the second topic I wanted to briefly address. Let me, in the meantime, check if there's. The second topic I wanted to address was the actual algorithm. So I want to also introduce this to my colleagues in linguistics and cognitive science, and also sort of like advertise this a bit. It's like the transformer algorithm is actually an interesting algorithm, also from a linguistic perspective, and we can actually, as linguists, productively interact with it. So I gave you this scheme of self-supervision, and then in the middle there's this language model. Now that here it's just a few colored blobs, but in reality, it's of course a pretty complicated algorithm. So here's a diagram that is the best summary that I've seen of all the little steps, all the little operations that are happening in the transformer diagram. Of course, and I want to focus then today on what is the most interesting part for us here. That is what you find here, and then you have something called Q, K, and V, and these Q and K and V stand for query, key, and value. And so forget about this diagram, but let's look at a linguistic example. Suppose that we have a sentence: the journalist talked to Sarah about book, and there's a mask there. So basically the language model has to predict what word do you expect at the position that we have masked. Is it her or is it his? How might a language model that has this task solve this? Well, the solution that the transformer is giving us is basically saying, like, every of the words, or rather, sometimes it's parts of words, so we call them tokens. Every token becomes its own little computational device, and every token has the task of collecting the information it needs to make such a prediction. So this whole process starts at the green token here. For the mask, it needs to decide: do I predict her here or his here? And basically what we want this token to do is something like, it send out a query and say, like, hey, is there a female human adult antecedent available for me? Or is there a male human adult antecedent available for me? Right. So it sends out this query through to all of the other tokens that are themselves collecting the information they need to perform their task. And in fact, these red little tokens, and their task is to actually send out a key where journalist says, I'm a male or a female human adult possible antecedent, and the key that looks at Sarah says, I'm female human adult antecedent. And now the query and the key can be compared, and when they match, and we have to define that mathematically, of course, when they match, only then is the semantic content from the red tokens being sent to the green tokens, and that semantic content is in a row of numbers that we call the value the value factor. So this process that I've sketched here for you in more or less linguistic terms is what's called the multi-head attention mechanism. And this is happening in the transformer architecture over and over and over again. In fact, you can think of transformers as being stacks of many different layers, and at every layer there are many different tokens, and each corresponding to one particular many different nodes corresponding to one particular token, and everywhere they're doing the same game. So there's all the time there's each of these nodes is sending out a query. Other nodes are sending out keys. If the keys in the queries match, then they exchange the value. And they do this over and over again. And one thing that has happened is that this architecture has been scaled up enormously. So whereas in this diagram I could only fit 4 layers, the ChatGPT actually has 196 different layers, and here I could only fit 5 what is called heads per layer, but in ChatGPT I think there's also 196 heads per layer. So the scale has just become enormous, but what it's doing over and over again is actually sort of repeat this trick. Now again, this sounds very different from what we find in the human language system. But I want to say once more, don't rush to conclusions about the differences in the architecture between humans and LLMs, because it's clear that these models are not cognitive models. it's clear that pretty much none of their components are actually motivated by results from brain sciences. But these models are trying to solve a very similar design problem, and they might actually converge to very similar solutions. So one of the things that we found, and here I cite some work from some nice work from our colleagues in Munich, Barbara Plank's group, is that we can actually, from the internal states of those trained transformers, we can actually distill parse trees. We can distill syntactic trees. In this case, they used what's called a DEP probe, a dependency tree probe. They could actually sort of like extract dependency parse trees of those sentences. So these models might actually be solving quite similar design problems as the human brain is solving when it's trying to learn a language, even though they are trained on massive amounts of data with an algorithm that is not particularly similar to the human brain. I'm going to skip this little demo, but if anyone is interested, we actually have done ourselves quite a bit of work on sort of like developing tools with which you can analyze these attention patterns. And there's a new technique that we've just published called value zeroing, and we have a demo online that is at the Hugging Face demo website, huggingface.co/Amsterdam NLP. You can find a value zeroing demo where you can actually sort of see what the effective attention from one word to another is at all the different layers of a number of large language models. Okay, the final two innovations that I wanted to talk to, I'll go a little bit faster. One is the third one is this what they call in-context learning, and here there's actually a very nice direct connection to linguistics, because this really goes back to some extent to the work test that everyone in linguistics knows about, of course, which is defined by Jean Gleason in the 50s. And which was really a test of what we now would call zero-shot or few-shot generalization. So zero-shot and few-shot generalization these days are defined in natural language processing and machine learning as the ability to generalize to a new pattern without having seen, so zero-shot would be without having seen a single example of the target pattern, and few-shot generalization would be to generalize to a new pattern based on just a handful of examples. And the famous paper that introduced GPT-3 was actually called "Language Models of Few-Shot Learners." And one of the examples in there is directly a work test. So they played with the prompt to do a fardoodle, means to jump up and down really fast. An example of a sentence that uses the word fardoodle is, and then GPT-3 continues, "One day when I was playing tag with my little sister, she got really excited and she started doing these crazy fardoodles." So you see that it knows how to apply the rule to generate English plurals just fine. And this idea of giving one or a couple of examples of a pattern that you're interested in, that has become incredibly powerful. And we call this these days prompt engineering. And this is actually become a very crucial human skill to interact with these machines. And one thing that's interesting is that that designing good prompts actually now is really the way that people are using to turn a general purpose large language models into language technology for specific purposes. And so here you see actually a little fragment of the instructions that the people at Microsoft have typed out for one of their chatbots. They're called GitHub Copilot, to actually perform its task correctly. And so they actually address it in English, telling it, "You are an AI programming assistant. When asked for your name, you must respond with GitHub Copilot. Follow the user's requirements carefully and to the letter." And all of this is prefixed to whatever you will type in, and to turn that chatbot into sort of the well-behaving chatbot for the particular circumstance. All right, the final bit of the final big innovations that has made ChatGPT possible is called learning from human feedback, of reinforcement learning from human feedback. And I can be very brief there. But so what the OpenAI did is they actually collected a lot of example conversations with human annotators. So they actually did the work of getting bringing people into a lab and actually interacting with the chatbot and writing down things, annotating, creating corpora. Note that is really linguistic work. That is corpus creation. That's something that our field has been working on for decades. And then what they do is, like, once you have this, they collect this, they fine tune the model on those example conversations. And the other thing they do is they ask human annotators to annotate the output of the large language model and to put a ranking on there. And then they use this sort of ranking results to do what's called reinforcement learning. So they learn from human feedback. The humans annotate their preferences. Based on those preferences, a so-called preference model is trained, and that is then used to sort of fix the large language model even further. Okay, so wrapping up, what does this all mean for cognitive scientists and linguists? Do these models have relevance for our theories? I would say yes. There's a lot of relevance because of this situation. We have this. We now have a new model species that we should really take advantage of, and we can test whether the theories that we develop for the structure of languages, whether they also apply to these other sort of linguistic creatures that now exist in this space as well. At the same time, there's also still a lot of worries in the use of this technology in society. We have worries about the truthfulness of these models. So one thing we've what was implicit in what I explained to you about innovation 1 and 4 is that these models are not actually optimized to be truthful, but they are optimized to be plausible and to be pleasing. And the truth is really a side effect of these two optimization problems. And so we see that they still produce hateful and biased contexts. So we worried that they might be used to generate disinformation. We're worried that they cause economic disruptions we're not happy with. We're worried about the concentration of power in the hands of big tech that this will lead to. We're worried about surveillance and privacy and carbon footprints. And there's an awful lot of work going on right now, including in my lab, on addressing these worries. We're trying to sort of actually build a new generation of models where truthfulness is a key, as a central design feature. We're trying to find ways of fighting undesirable content in these models. We're trying to sort of understand the dynamics of the spread of misinformation and how they will interact with these kind of models. And all of these topics are topics that are very where linguistic expertise can be really of great value. So in conclusion, we've seen breathtaking progress. We've seen a truly disruptive new technology emerge from a field that has been studied since the 1940s. It's disruptive, but it's not magic. It's based on 4 innovations. And I'm emphasizing it's not magic because we can actually do this for other languages than the languages that are currently in the training set as well. There are all over the world's efforts happening right now. Linguistic concepts have played a key role that is sometimes underestimated in these developments. And I think there are still many opportunities for linguists to actually contribute to deep learning, in particular when it comes to making these models more interpretable and making their deployment more responsible. But there's also great opportunities for linguistics itself, because we now have a new model species. We have new devices that have linguistic capabilities that we never thought would be possible. With many differences with how humans operate, but also many opportunities to test and develop theories about innateness, learnability, and neural subsets of language. that I hope the field will take advantage of. All right, thank you.